in 1850s, this technology was actually discovered. So this is nothing new. What Micatu has done is we've commercialized this, and we really brought this to the grid so that we could bring this higher level of accuracy, isolation, safety to it. And so if you think about how Faraday works, it's really a pretty straightforward principle. And the fact is that you have a piece of glass that's basically reacts in a magnetic field. So we'll shoot a photon through this, and the way the photon comes back out changes, and that change is proportionate to the actual current, which is proportional to the magnetic field. One of the exciting things about Faraday measurement is that we have a huge dynamic range. So what do I mean by dynamic range is that we can measure from 10 amps up to 150,000 amps, and the sensor is essentially immune to it. We've done some really exciting testing, and this is some information I think Amanda can share with anyone who's interested about what we can measure and how we can actually measure the large dynamic range and still not to get saturated or actually have the sensor be damaged. Going on to slide 14, we measure voltage by something called Pockels Effect. So a Pockels Effect, once again, was actually discovered in the late 1890s. And essentially, you can take a EO material, shoot a photon through it, and as that photon actually goes through this material, you can kind of think about it this way, and this is the way I'd like to explain it, is that the actual atomic and stoichiometric geometry is just a fancy word for the way it's made inside, actually starts to kind of go like this, right? So the photon's got to travel through this moving atomic structure, and it actually takes the light and slows it down and speeds it up. By using some polarization analyzation, essentially we're just setting it, we can actually get a nice sine wave that comes out that's proportional to the E field. This E field coming out is once again proportional to the potential of the line. So the exciting thing about this, if you think about it, is we're fully isolated from the system. So we shoot a photon through this piece of crystal, piece of lithium niobate, a field goes across it, that field actually changes the way the photon travels through it. We can detect that change, and we can actually measure the electric field. The great thing about this too is that being a field sensor, I talked about this earlier, is the actual harmonics content. So we can actually measure much deeper harmonic content, which is very important for the grid of the future. And as we put more of this renewable in, is power quality, right? There's a lot of conversion from AC to DC.